All right, hello everyone, and welcome back to Historical Geology 1404. Today is Lecture 6. We are continuing in Module 2, learning more about life, the history of life, the development of life, how it changes, and today, how it interacts with its environments. But before we get started on that, what's up? Everyone good? Anything we want to talk about? Yeah, Artemis did its flyby of the moon. Which is super, super exciting. So many cool pictures. Have you guys seen some of the pictures coming out from this? Yes, I watched as they were naming those craters, and I cried. Yes, I cried. So for some reference, the commander of the Artemis 2 mission is named Reed Wiseman. He's been an astronaut for, I want to say, about a dozen years now. But a few years ago, his wife died from cancer, leaving him a single father of 2 daughters. He continued being an astronaut and raising them on his own, which was not easy. His wife's name was Carol. And I don't know how much you know about the astronaut program, but astronauts are extremely close. They spend almost every moment together from the minute that they join the program. And so their families get really close together. And so Carol wasn't just, his wife, she was a member of the astronaut family as well. And so they were up there, and the closer they got to the moon, the more resolved pictures they were able to take. They realized there are 2 craters on the moon that have never been seen before, and therefore were unnamed. And so the Canadian Space Agency astronaut, Jeremy, got on the line to NASA and said, hey, we'd like to name these. And NASA was like, yeah, sure, go for it. So they said, we want to name the first one Integrity Crater, after the name of their ship. I was like, yeah, that makes sense. And then he said, and this is where I started tearing up, we lost a member of our family a few years ago, and we would like to name the second crater Carol Crater, after Reed Wiseman's wife. And you can actually see on the camera footage of while he's reading this inside, like Reed immediately starts crying. And then everyone in the spaceship starts crying and hugging each other. And then everyone in NASA starts crying. And I was crying, and I'm sure that millions of people around the country were crying. I'm hoping that brings out some emotion in people, because it is truly touching. And honestly, I look at that as a wonderful example of why it is so important to participate in these sort of things as a community. Because it's this that brings us together. Loss brings us together. Exploration brings us together. And we need to capitalize on those things, because they are beautiful. As difficult as some of them may be, they can be beautiful and bring people closer together as a consequence. But yeah, that happened. It was wonderful, beautiful. Lots of amazing images. There's a particularly famous image of Earthset over the moon that is going to get spread around for a big, long time. It is a fantastic image.
It's so cool watching it, like as they pass the moon, you can
Yeah.
see it. And then
Yep. As they went behind the moon, there was 40 minutes of no communication with them, because radio waves can't go through the moon. Oh yeah. Yeah, they're about 80,000 miles away from the moon now. About 200,000 something more to go. Less than that, maybe, I think, actually. 180, 190,000 something. But yeah, they're set to land in the Pacific Ocean on April 11th. Okay, so total trip time, 10 days, in a vehicle the size of 2 minivans. If you can imagine living with 4 people in an area the size of 2 minivans for 10 days, you've been in that vehicle. This is why they train for years, so that they know how to move efficiently and not, bump into stuff, not bother each other, how to live together in that little environment. These people have been training together for years so that they are the best of possible friends for this mission, because the last thing you want is for someone to crack and start wailing on the other guy because of something that he does, How to fight somebody in zero gravity? Yeah, I mean, laws of momentum, right? You punch somebody, you fly backward, because your force is being applied to them, and the force of their body absorbing your energy is going to put some into you. So, yeah, there's a lot. Luckily, it doesn't come to that. There have been a few tense moments in space, for sure. But as far as I'm aware, there haven't been any actual, all-out crew fights. Not yet. But we very carefully pick our astronauts and train them to avoid situations like that. Yeah, very, very cool stuff. they're on their way home now. Something else that we realized when we got up there, and with our actual like good camera technology we have versus the last time we went to the moon is not gray. The moon has, it's got some black and gray, but it's also got a lot of green and brown. The moon is also, it's multicolored because of all of the minerals it's made out of and the effect that ultraviolet radiation has had on those minerals over time, changing their color slowly across the surface. It's going to be incredible. Like, being a geologist right now and interested in the moon is fascinating. I actually reached out to a couple of the geologists at NASA and asked if there was any research projects that I could help with along the way. We'll see, though. I'm sure that they've got their hands full with all their data, and they may or may not see my message anytime soon. Let's see. What else? Oh! On the subject of space exploration. Each year, the White House releases the president's preferred budget for each department and agency. You know where I'm going with this. The president's budget request for fiscal year 2027 came out and includes a 47% cut to NASA science. It gives a lot of money to the Artemis program, which it absolutely should, but it almost slices the science budget in half, which would effectively cancel 40 missions that are being planned right now across our solar system, going to Venus, the moons of Jupiter, and Saturn, further out to the asteroid belt, to Mars, and it would include canceling officially the mission to bring the Mars samples back here, all of that. That's not only the only, that's not the most, I mean, that's pretty bad, but it's not the only bad thing about this budget request. It is almost exactly word for word the same budget request that was put through Congress last year. So what happens here legislatively is the budget submits this, hey, this is what I would prefer our money to go or not go. Then the Congress has to pass that budget to approve it because we live in a system of checks and balances most of the time, unless you sign an executive order for something. And luckily, last year when they submitted this proposal, Congress almost universally turned it down. I want to say it was like 80-something% to 10-something% against, right? So they shut it down fast. I think it was one of only 2 bills that went through Congress that both sides of the aisle agreed that much on last year, okay? This budget request is the exact same wording as last year's. And when I say exact, I mean in an unfortunate way too, because a lot of the wording still refers to it as fiscal year 2026. It still is referencing, in this year's budget, it is referring to itself as a request for last year's budget, which means one of 2 things to me. Either they did not care enough and they handed it off to some underpaid intern and said, hey, brush this up and submit it again for this year, which is not good, or they just told an AI to do it. Hey, assemble some sort of fiscal year budget that aligns with our parameters here based off of last year's budget request. Because there are so many errors in this thing, including referring to missions that were already canceled and referring to itself as a request for last year's budget. So not great, not great. But what we don't want is for Congress to think, oh, well, this is a silly thing. We already turned this one down and not pay it any heed. Because if people just ignore it, it might actually pass. People need to actively oppose it in Congress. So if you feel as strongly about this as I do, please reach out to your congressman. If you don't know how to do that, I can send you a link that has a pre-assembled letter saying, hey, we are concerned about this, and all you have to do is put your name on the end, and it'll send it off. Go ahead and let me know, and I can send you that link. I've actually already messaged a few people in our congressman's office that I've spoken to before. Every now and then, they'll call me, or I'll call them about different scientific subjects. So I've reached out to all the people I know over there to let them know I'm concerned about it. So if you would like to join that cause as well, go ahead and let me know, and I can point you in the right direction. What else? Actually, I want to hesitate on that for a second. Funding is always a problem for any scientific objective, right? Where should funding come from? Where does funding come from? There's the obvious answer, right? NASA. That's taxpayer money, right? For the most part. Where else do you suppose this comes from? Huh? Private investors, absolutely. The private space industry is massive. NASA got, what was it, somewhere around ballpark $40 billion last year in operations. But there were more than $350 billion spent on space. Clearly, NASA is not the biggest player here, right? Private industry is investing a lot of money into space. So yeah, that's a massive thing. What else? There's this thing called the National Science Foundation, right? NSF, which historically has put a lot of money into funding really cool science projects, right? Like if you have a thesis or a dissertation or a research subject, something you'd like, hey, I think there's this really cool thing in the rocks of Iceland and I want to go and prove that it's there or not. You apply for an NSF grant, and if the people that are in charge of handing out that money think that it's a valid exercise, they'll give you the money to go. That's been the nature of NSF for years. And so I was talking about the president's budget request to someone the other day, and they mentioned, well, it's not really within NASA's purview lately to fund science, things like that. They should be focused on building up the American science industry, or space industry. Like, well, I would argue that the American space industry should probably be something that is overseen by a government agency, but mostly invested in by private organizations, or else you'll end up with an oligarchy in space, right? Which we don't want. I think that government and taxpayer money should go into science because that's where a lot of our long-term investments come from, is investing in science, right? Let them worry about the commercialization so much. Let us worry about how to do it right, okay? Regulation, policies, things like that, that should be the role there. So, but this person I was talking to, they said, well, let that Science Foundation, the NSF, let them fund things like all of these science missions if they think that it's worth it. But here's the thing. I remember how I told you that NASA was experiencing, if this budget request passes, a 47% cut, a slash to their science budget? NSF, if that budget passes, will get a 54.5% slash to its budget. So the argument of let NSF handle it, that doesn't work either. Science is under attack from a lot of different directions here. It's getting slashed. Oh, and you know another thing? You know what part of NASA will get absolutely 100% slashed if that budget request passes? The Office of STEM Engagement. No more NASA people going to schools. No more space education from NASA. No more engagement of any kind for education purposes from NASA. That's what the passing of this bill would mean. They don't even get that much money, not compared to the other divisions of NASA. But if this budget request passes, it would all be gone. So like for this big space science event I'm trying to throw next year to celebrate the 50-year anniversary of the Voyager spacecraft launch, I'm reaching out to NASA. I'm trying to work with NASA to have at least some materials brought here for that event. If not, someone specifically from NASA to come and speak and things like that. This budget request passes, that's all gone. They can't do any kind of engagement like that anymore. So there's a lot of things that go into this that we can't let slide. All right. Okay, so the objective part of my brain wants to say things like defense. The cynical part of my brain that sees how our president behaves wants to say golden ballrooms. There's $300 million going into that ballroom. It's a 9,000 square foot ballroom that they're adding onto the White House. It's $300 million so far. Now, granted, they say that that money is private money, like private investment money. I cannot verify that. I'm not in the position to verify that. Not taxpayer money. Sure, but that still demonstrates a distinct lack of wisdom and priority in funding and spending in the White House, in my opinion. If time and money of any kind is going into building a golden ballroom for the White House, and we are slashing education and science exploration money, I think that there is a lot of misaligned priorities. So, however much I agree with Trump on some of the choices he's made, I disagree with him pretty strongly on others, clearly.
Because science isn't profitable.
That is an argument I have heard a lot of. Science is not profitable.
Immediately.
Profit is the domain of private industry, not government.
Yeah, that's what I'm saying, like immediately.
Yeah. Science has inherent value without tangible benefit.
I agree.
Yes, it's very true. But which is why that should be something that is invested in by a non-profit-oriented organization like NASA. If private companies think that there is profit to be gained by exploring, then they will, with their own money, or money that they apply to the government for, and the government decides is a worthwhile investment. But the government's priorities are to maintain the safety, stability, and health of their citizens. And science is the way that we do that. What good would going to Venus provide for that? Well, it would give us a lot of information on what may occur to a planet given certain environmental conditions. But also, how many times has investing in some kind of obscure science yielded some sort of medical benefit? How many plants and animals and insects do we know of in the rainforest or from the bottom of the ocean that we now have some sort of medical benefit from, right? We won't know what potential benefit there may be to the American people or the people of Earth from the atmosphere of Venus unless we go and investigate the atmosphere of Venus. There is value in doing these things without making a profit off of it. There's value in just the knowing. So, all right, 15 minutes later, I step off my soapbox and we can begin our lecture, unless you guys have anything else to add or ask. No? All right. Grab a drink and then we can talk. While I'm taking my drink, remind me what we learned last time about the ways that life changes. What did we learn about the ways that life changes? You said two words there, adapt and mutation. The change is mutation in DNA. The result is adaptation to an environmental parameter, okay? That adaptation to that environmental parameter is going to be more of the subject of today. Last time we talked a lot about mutations, adjustments, alterations to your DNA. Each one of these strands of DNA contains trillions of lines of code, I don't remember the exact number, but lots of lines of code that dictate every aspect of your physical self. From the color of your hair to how quickly it grows, to your fingernails, to what is your metabolism like, how strong is your immune system, the color of your eyes, things like that. Everything, okay, are dictated by this DNA. And any change to that, remove that, or change it to another pair, okay, and you're going to end up with a different characteristic. That is mutation, and that is caused by radiation. Most commonly radiation from the sun, but with exposure to acute radiation sources like a nuclear weapon or a nuclear bomb or anything like that, or even just exposure to a lot of uranium ore, you're going to end up with out-of-control mutations, and that's what leads to things like cancer and death, okay? These mutations, though, they are constantly ongoing. Hard for us to see them over time, but still present. Okay? Still there. And they build up over time and make changes. And those changes, if positive, they give you an advantage in an environment or a new changing environment, perhaps. That is where it becomes an adaptation. Okay. So, why adapt? In what circumstances would a mutation be considered positive? Remember the example I gave you of the wolf with long claws? Or no claws, things like that? Well, in an environment where you don't need claws for your prey, if you're only hunting bunny rabbits, you really only need your teeth. But if you're hunting larger things like deer, your claws might actually come in handy, right? So the food, your food source, how stable your food chain is and what your primary food source is a huge environmental factor in what could dictate a positive mutation or a negative mutation. Remember, this is not happening as a result of conscious thought of the animal. There is no point where the animal's like, you know what would be really helpful here? Longer claws. And then they grow longer claws. No, that doesn't happen. That's not adaptation. It is not purposeful. Adaptation, mutation, is random. And only when those random changes yield a positive result does it become an adaptation that we see carry through the species. Okay? So, your food, that's a big factor. Okay? Your food sources change or another thing moves in and is competing with you, you got to adapt or your species dies off. Okay? So many more species of things of life on Earth have died than are existing right now. I don't feel confident giving you a number, but if I had to guess, I'd say maybe 0.1% of all living things on Earth right now represent the total number of species that have ever lived. Everything else has died off over time. Okay? New climate conditions. Okay, well, what does that mean? Changing temperature or chemistry, right? Did you guys know that if you change the temperature of the ocean by 1.5, 2 degrees, you kill off half of everything that lives in it? Yeah. Do you know that's happening? As our air warms up, slowly, so does our ocean. What about acidity, the chemistry of your environment? Air chemistry, that changes based on things like quantities of greenhouse gases. We can still breathe it, right? I mean, in really, really densely polluted areas like London or Salt Lake City, you see negative health effects from breathing that in over a lifetime. But for the most part, we're all right. We deal with it. What about if the chemistry of the ocean changes? There's this thing called ocean atmosphere flux. It's a state of balance between the ocean and the atmosphere. You change the chemistry of the atmosphere, the chemistry of the ocean changes as a result. We add more carbon dioxide to the atmosphere, more carbonic acid is generated in the ocean as the ocean absorbs the carbon dioxide from the atmosphere. You increase the acidity of the ocean, what's going to happen? Let me tie this into a concept you learned before in 1403. What minerals did I describe as dissolving real easily in carbonic acid? There was one in particular. You even threw some acid on it in our lab. Calcite. Yes. Calcite. Yeah. Calcite dissolves real easily in the presence of many acids, including carbonic acid. That's how we get cave systems underground. Layers of calcite-rich limestone dissolve in the presence of the carbonic acid flowing through the groundwater. Okay. What are seashells made out of? Silica or calcite? Calcite in the warm water, silica is in the cold water, right? What happens if I increase the acidification of my ocean? What happens to those animals? They die because their shells either dissolve or become so brittle that they cannot sustain the animal. Coral reefs collapse under their own weight. Clams, nautiloids, anything with a shell that uses calcite, they die off. We are seeing this right now. The ocean is currently both warming and acidifying as a result of the increase of carbon dioxide in the atmosphere. We are living in what we refer to as a mass extinction right now. The quantity of things that die off every day technically qualifies our current age as a mass extinction. We lose dozens of species a day between the ocean and land. Okay? We'll talk more about extinctions later on in the term. Next week, actually, I think. But yeah, these are all factors that go into changing what your climate, the environment looks like there. Okay? Predation. What if a new predator walks into town, right? You get a new kid on the block with a bigger, badder set of claws or teeth, and that's going to upset the balance of your ecosystem. Okay? You got to adapt to that. There is something that you'll see me refer to in when we discuss how life has advanced through time, called the evolutionary arms race. You guys know what an arms race is? The length of your arm? No. No. Not arms like this. I'm talking arms like bang, 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 bang. Right? Like
how fast?
yes. Why couldn't the T-Rex sell rifles? He only had small arms. Yeah. Okay. But Ivan, what were you saying? You were saying something about the evolutionary arms race? What is an arms race? Yeah, the classic example is the Cold War, okay, where the United States developed nuclear weapons, and then shortly afterward, the USSR developed nuclear weapons, and so the US made more of them, and so the US made bigger ones, and so the US made big ones, and went back and forth. And the only thing keeping either side, when it got real bad, from shooting at each other was the fact that they knew that the other side had it. This is an arms race where your only defense is a bigger, badder gun. Okay? Well, in evolution, we see similar sort of things. Predator comes on the scene with bigger teeth. Prey adapts to have thicker shells, or horns, or spikes. And so your predator needs to evolve longer arms to flip you over so that you don't get spiked in the gut when you try and bite them. Well, your prey develops under armor, or more flexibility, or a tail that can defend itself from the side. We see this through time. This is called the evolutionary arms race, and it's often a result of predator and prey relationships. Okay? Competition. What if that predator comes in and the predators that were there before now need to compete with that one for food? What's their only option? Adapt. Or move. Go somewhere else. Or die. Right? Either one of those is a valid option, and dying is one that we see quite often. Okay? You can't compete and you can't change fast enough. Species goes extinct because you can't get your food anymore. You don't eat, you die as an individual, and enough individuals die, species can't continue. Okay? Now, there's a word called habitat. A habitat is an area that is inhabited by life. Okay? So there are many types of habitats. We could describe this room as a habitat. It is an area inhabited by life, correct? Do we inhabit this space? Temporarily, yes, yeah, for 3 hours or per term or per day. It's 6 hours a week unless you come in on extra times to study, right? Which is always appreciated, always an option for you guys. Okay. Couple more terms I need you to learn here. Ecology. Ecology isn't just the study of life. It's a study of life as it interacts with its environment. Okay. So there's a difference between a naturalist, who is someone who kind of generally holistically studies science. I am a geologist, someone who, for the most part, studies rocks, minerals, the ways that they come together in our Earth, and the ways that they, nowadays, right, and my particular interest these days is how those laws apply to other worlds, right, like our moon and Mars. You've got biologists that focus entirely on life, how things work down to the cellular level. Ecologists study that life, the environments that they are in, and all of the interactions that take place in it. So, did you have something? No? You're good? Okay. So an ecologist is someone who is kind of a specialization of that type of science from biology. Okay? Niche. A niche is a word that means a specific domain or space within ecology, okay, within that environment that life is living inside of. Think of a niche as kind of an apartment. If ecology, if an ecosystem is an apartment building, a niche is an apartment in that apartment building. So every aspect of that ecosystem is filled by some kind of life. You've got your apex predators, you've got your your browsers, you've got your grazers, the ones that eat grass off the ground. Your browsers just kind of eat stuff off of trees and bushes, right? You've got your burrowing animals that eat your insects and act as the food for the smaller predators. All of that. Each one of these niches or spaces, think of as an apartment in your apartment building. Whenever one is vacated, aka something goes extinct, what do you suppose happens? Someone else moves in, like that. Do you guys know how bad the apartment situation in Odessa is? How many of you live in an apartment? Oh, well, I usually have at least one. I've lived in a few apartments, okay? In Odessa, the apartments, that's a rough situation. Apartments are expensive, and the minute one opens, it's immediately snagged up because there's usually a wait list at every apartment building. There are more people that need places to live here than have permanent places to live. And the real estate system here is pretty messed up because people know that they can charge anything that they want to oil field workers and the oil companies will pay for it. So that makes those of us that don't work for oil field companies in a tough spot because it's so expensive to try and live here, right? Cheaper than a lot of places, but still pretty expensive because they hike the prices up to take advantage of the oil field. Okay. Yeah, when one of those apartments in our ecosystem is left vacant, something else will adapt to fill it. Okay, so that's a niche. Okay, a space in an ecosystem. Okay, population. When I say population, it is a, oh, I'm sorry, I forgot that I wrote all of this up there. Let me erase this. A population is individuals within a species in a given area. Are we here in this room members of the same species? Yes, we are. Homo sapiens is our species. Doesn't matter how different we look from each other, we are members of the same species. We just have ancestry that was separated by geographic distance. Nevertheless, we are still part of the same root ancestor and still part of the same species. So, a community, then, is what we call a group of organisms from a variety of species in that given area. Okay? So if I were to, again, think of this room. Okay? This room is an ecosystem, a habitat, within which is a community of organisms. Right? There are two populations within this room in our community that we can see. What are the two populations that occupy this room? Frogs and us. There's probably also some bugs, spiders, things like that. We can't identify those. They're probably here, though. Some of you may have brought them in on your bags. I don't know, right? Okay. Yeah, you're going to get all creepy crawlies when you put on your backpack, right? No. So there's at least two confirmed populations in this room, making the community of organisms in this room, which is our habitat. Are you following how all of these terms work? Okay, great. Because I'm going to be using these terms for the rest of the course. Okay? When I say community, all of the organisms in an area. Population, just the one species in that community. Okay? Niche, a domain occupied by a group of organisms that fills the need. Okay, that fills an aspect of that ecosystem. Okay. All right, let's talk about the different environments that we see around the Earth and how those might affect the organisms that live there. How organisms might adapt to live in those environments. Okay. This is a general environmental trend map. Okay, so right here, this is our equator line. You can see where it's green, that's tropical rainforest. Our tropical rainforest is generally congregated around our equator line. Why? Remind me what the convection cells in the atmosphere are doing. Hot air goes up at the equator, moves outward, but what's it doing when it gets high enough? It cools down and rains out a lot of moisture. So not only is it hot at the equator, it's also very rainy, which promotes a lot of plant growth. Those convection cells carry the air north or south of the equator, and as it rains more, it gets cooler and drier. So by the time it gets up here and down here, it is cool and dry air, and that is where we get deserts. So we have tropics here at the equator, deserts about mid-latitude, and in between, transition zones. So out here in Africa, for example, we'll go from tropical rainforest to Serengeti to desert. Going down south, tropical rainforest, Serengeti, desert. Okay? Same thing over here in Africa, Australia, excuse me. There's not really so much rainforest here. There's a lot up here in Papua New Guinea and such. But you get your deserts out here, and then your kind of semi-arid, semi-deserty areas. And then you've got some temperate forests out here, and you've got some grasslands down here. But you see the same sort of phase. North America as well. Okay? So these are the trends that we see in environment going from the equator to the north or south. The atmosphere plays a big role in that. Okay? The atmosphere is a major environmental factor, not only in the trends of environments that we see trending from the equator to the north or south, but also for every environment in general. Okay? What is our atmosphere made out of? What are the dominant gases in our atmosphere? Nitrogen, oxygen, huh?
Carbon dioxide is only like 0.4%.
Yeah, we're going to count carbon dioxide as oxygen here.
Helium, right?
Any other ideas? So I heard nitrogen. Nitrogen, do you know that nitrogen is most of our atmosphere? 78% of our atmosphere is nitrogen.
21% or
Yeah, oxygen. It's going to be oxygen. Now, this doesn't just mean oxygen. This also means carbon dioxide, carbon monoxide, water vapor, any oxygen in the atmosphere. Okay? That leaves 1 extra percent, because that makes 99. Huh? Other? I mean, kinda, yeah. But most of that other is taken up by one other gas.
Or is it like one of the noble gases?
Yeah, it's argon. Okay? It's argon. Where's argon here? Right there. Number 18. Argon in concentration is dangerous because it shoves out the oxygen in an area. So if you're in an argon environment and you're breathing that in, you will suffocate and die, right? And argon leaks out of the ground more or less from different areas, okay? But we can ignore that for now. That's not really relevant to the conversation. Oxygen, we need to respire, to breathe, okay? Oxygen, something that plants exhale as they respire, okay? They spit it out, we breathe it in, we have the symbiotic relationship. It's great. Well, until you cut down enough trees and then it becomes a problem, okay? All right. So another function of the atmosphere is it traps heat here. So any solar or cosmic radiation has to get through a couple of vault doors, you could say, okay, before it reaches us. It has to get through Earth's magnetic field. Then it has to get through the ozone layer, which is our upper atmosphere, which is made out of types of gases which we refer to as ozone and block a lot of that radiation. And then it has to make it through the whole rest of the atmosphere before it hits your skin and gives you that sunburn or tan. Okay? The more greenhouse gases there are in the atmosphere, the more difficult it is for that radiation to make it to us. Why? What are greenhouse gases? Yeah, what is a greenhouse gas? We talked about this when we learned about glaciers in 1403. What is a greenhouse gas? What constitutes something being a greenhouse gas? Yeah. It's a larger molecule, okay? So as it's up there in the atmosphere, it's going to block or absorb a lot of the energy from incoming radiation. So what that means is, here I have surface of the Earth. Here's an exaggerated thickness of atmosphere. Solar radiation, super high wavelength, right? Super high energy. Blue light, right? Then it hits our atmosphere, and as it does so, it's going to lose some of that energy and take on a longer wavelength, becoming more closer to the red spectrum of visible light, okay? But when it's hitting us straight on like this, it doesn't lose much energy, and so we get a lot of heat there. That's why at the equator there's a lot of heat, less cross-section of atmosphere for it to go through. That's why when you look and the sun is straight up above us during the day, the sky is blue. We are seeing blue wavelengths of light come through our atmosphere. There are still high energy wavelengths. But at sunset, or at the poles, where there is more cross-section of atmosphere to go through, if the sun's way off over there, sunset or sunrise, the sunlight is coming through a thicker cross-section of atmosphere to reach my eyes. Those rays of light lose more energy to atmospheric particles and become closer to the red spectrum. It's so interesting, isn't it? Because in art, we are taught blue means cold, red means hot. In physics, blue is hot, higher energy. Red is cold, lower energy. Interesting how those flip. Every couple of weeks, I'll model for our art class over in the State Hall. And I had this conversation with them. I was just sitting there. Believe it or not, it's hard for me to just sit somewhere quietly. If there's a scientific thing, I need to share it. So I'm just sitting there letting them paint me, and I'm just like, blah, 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 about science stuff, right? And I was talking to them about this, and they're like, whoa, what? And I explained the whole process to them, the whole concept to them, and it kind of blew their minds that they use blue to cool a picture down, but I look at it and I'm like, oh, that's a hot color, right? It's pretty cool, pretty fun. I love sharing that with them. But what does this have to do with greenhouse gases? Greenhouse gases are larger particles in the atmosphere, which means that they absorb, for more greenhouse gases, they absorb more energy, which, what does that mean here? If my energy particle, my wave of light, or my radiation particle doesn't have enough energy to leave the atmosphere again, it won't. It'll stay here. So that radiation bounces off Earth's surface and then doesn't have enough energy to leave again. So it keeps zing, 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 zing until it loses energy here. In an environment with few greenhouse gases in the atmosphere, that light will hit the Earth's surface and leave again, a lot of it. So, as we increase the quantity of greenhouse gases in the atmosphere, we retain more solar heat, building up the temperature of the planet. That's the situation we're in right now. That's what every global warming cycle throughout the history of the Earth has been, associated, at least in part, with greenhouse gases. Now, what is the most common greenhouse gas? Water vapor, H2O, very large molecule, hangs out in the atmosphere a lot. The more water vapor we have, the more heat we retain. Well, water vapor is not bad. What's another common greenhouse gas? Methane. Yep, we produce a heck of a lot of methane, not only through the production of fuels and all of that, but also domestic animals. Is that what you were going to say?
Yeah, livestock.
Yeah, livestock. Yeah, domesticated animals, cows. Do you know how many cows we have just in the U.S. alone?
I'm going to take a gander. 8 billion.
8 billion? I don't know. I doubt that's true, but I actually have no idea. I was curious what you would say, though. Okay, I doubt it's 8 billion, because that's one cow for every person on the planet, right? But probably not. Nevertheless, I would wager across the planet, hundreds of millions of cows. And, we eat a bunch of them, and then a bunch more are born. They're constantly cycling. But you know what they produce? A heck of a lot of methane. There's a substantial movement to develop technology, you know where I'm going with this, to capture cow farts. Yeah, because they produce a lot of methane in the process of breaking down plant matter in their gut. Methane is the byproduct of the bacteria in their gut breaking it down. You capture those cow farts, you bottle it up, and you use it to cook your food. If I came to you with a bottle of cow fart fuel, how would you feel about that, right? It's not gone anywhere yet, because even though they produce a lot of methane, The technology to capture that, process it, bottle it up, and send it around is still very expensive comparatively, so no one's really doing anything with it. But they still produce a heck of a lot of methane. Another common greenhouse gas, the one everyone talks about, CO2, carbon dioxide. It's valid to think of this as a problem. It is a problem. If you look at the production of CO2 from humanity going back for the last 400 years, start with the year 1600 and go to now, you see a hockey stick progress line, right? So if this is time, and this axis is CO2 production, you see that exponential growth in the increase of carbon dioxide. Now, is that all us? No. Is a lot of it us? Yes. Yes.
I was going to say, isn't it like the carbon dioxide is only like 0.4% of the atmosphere? We only produce like 11% of it or something like that.
Yeah. Yes. But any amount that we put in is an amount that is not there on its own. So it has an effect. Even if it's a small one, it adds up, which is why it's taken hundreds of years for it to do so. But here's the thing. We are always building more cars. We are always producing more fuel. Those cars are always burning more things. We are always making more coal power plants. We are always doing this. We are always doing that. It adds up, and that's why it becomes exponential. Okay? So while it's a small amount of the atmospheric quantity as a whole, that's true, the add up makes a problem. Okay? And that's the situation we find ourselves in. Quantitatively, it's not much that we add. Qualitatively, it matters. Okay? All right.
Would you say that the Earth is overpopulated?
Overpopulated? By humans? I do not. In everything that I say, everything I advocate, be that space exploration and industrial development, be that reduction in greenhouse gas emissions, anything that I share with you in this class that advocates for change, at no point does it ever, or do I ever advocate for people to be any less than the main priority for those things. Humanity is the #1 driving motivator for what I believe in, and I think for what anyone should believe in. It's all well and good to say we need to take care of our planet, but we need to take care of our planet for us. Right? It's good to be considerate of our planet and not want to kill off stuff. We shouldn't do that. But we shouldn't want to do that because it preserves the planet for us. That may sound selfish at first, but without us, there's no one to care. If we just went bloop from the world right now, the world would be fine. It would keep on moving, trucking, right without us. But we'd be gone. And then there is no point for us, right? If we keep on the process that we are right now and we just absolutely ravage this planet and then somehow develop the technology to pick up and leave and go somewhere else, do the same thing to another planet, you know what? Earth will survive. It'll move on. Is it likely that we will ever destroy all life on Earth? No, it's not. Life has survived worse than us. Something you're going to learn in this class? Earth has lost 95% of every living thing on it before. Mass extinctions, gamma ray bursts from space, from supernovae, blasting this planet with radiation, absolutely annihilating it. Massive, massive volcanic eruptions that cover entire continents in lava. Asteroid impacts over and over and over that rip up chunks of our planet, throw them into space, so far that they land on Mars. Our planet has survived a lot, and life is still here. It's going to survive us. So, my driving, motivating factor here is responsible action for our planet, but the responsible action that will also lead to better survivability and continuation of human civilization. So to answer your question in the long way, no, I do not think the planet is too overpopulated. Is it very populated? Yes. What's the answer to that? What's the answer to the lack of resources? More efficient production. Actually investing in efficiency rather than investing in easier ways to get stuff. Honestly, I think we could do with a few less luxuries on our planet. Could people get by with one car? Sure. even if we just limited every person on this planet to 2 cars, we would eliminate 30% of all the vehicles. There's so many people. You may not look at it, may not know it looking out there, but for every person on this planet, like, so many people have more than 2 cars that don't need it, right? And even the people that have 2 cars, a lot of them have jobs or situations where they could get by with 1. And if I could magically go, boop, eliminate all of those unnecessary vehicles in the world, and all of a sudden have those resources available to more efficiently take care of our world population, we wouldn't have as many resource needs. We wouldn't have as many shortages. And a lot of our problems are, self-inflicted. War. When Russia went to war with Ukraine, started invading them, the most recent time, right? A few years ago. Do you know what? Do you know how that affected Australia? You wouldn't think that it did. Australia got most of its wheat from Russia and Ukraine. And as soon as they went to war, that wheat pipeline stopped. Which was poor timing, because Australia was and still is going through a field mouse epidemic right now. Their crops are getting absolutely destroyed by rodents over there and have been for a while. They're trying to contain it, but it's very hard to control a rodent problem. Okay? That's widespread across a country like that. So where do they had to get their wheat from other places, far more expensive places, and therefore there has been a wheat shortage and therefore an increase in the price of wheat products like bread in Australia as a result of a war on the other side of the world. Okay? So a lot of the problems we face that affect things like what feels like overpopulation is a result of our own poor choices as a species. Does that make sense? Great. Great. And bear in mind, these are the opinions and observations of just a fella, me, right? Make your own interpretations as you will. I don't expect you to leave as many versions of me in every opinion that I have. And I would be dissatisfied if you did, at least not unless you gave it the due thought. Come to your own conclusions, but I've been around. So I hope that at least my opinions or my considerations on these matters carry some weight. All right. Now, let's talk about other changes that can influence your environment. Topography. You guys remember when we did the topographic map exercise, Lab 5 and 1403?
Yes.
Yes. You enjoyed that? Is that a good one?
Actually, I thought it was the easiest.
You thought it was the easiest one? Yes, and therefore the most enjoyable, right? Yeah, so what you were looking at was changes in the elevation of a landscape depicted on a map. Well, the higher your landscape gets, the higher in elevation it gets, what's going to happen? Yeah, it's steeper. Sure, you'll probably get steep slopes, which will influence the kinds of the kinds of life that you can get there, because you'll have thinner soils or less adaptable soils, but also atmosphere thinning. The higher up you get, the thinner your atmosphere gets. Have you ever heard any stories of people that climb Mount Everest? What do they take with them?
Like an oxygen.
Yeah, they take an oxygen tank. Why? Because the atmosphere is so thin that high up you cannot breathe it without special training or some oxygen mixing that you can put into your lungs in addition to what's up there in the atmosphere. Okay? Also, as the atmosphere thins, what else happens?
It gets cold.
It gets colder. Your temperature drops. All of these factors are going to influence what types of things can live up there. Does anything live on the pinnacle of Mount Everest? No, it's a hostile environment. Matter of fact, it's difficult for people to get up there still. Do you know that there are still bodies up there on Mount Everest? People that have died up there, their bodies stay up there. Because just getting yourself up there and back is hard enough. You physically cannot carry someone else's body back down. Okay? So up there they remain. Which is very interesting when you think about it, because it's a perfect preservation environment. They're pretty much just frozen solid. They're peoplesicles.
Did you need to get like a permit?
To go up there? Yeah, you need permission from the Nepal government.
Do you need to get like a physical and stuff like that? Like, is it like an expensive
So the organizations, the guides that take you up there will often make you go through that sort of stuff because the last thing they want is the issue of a dead guest in their country. It does still happen, not as much as it used to because there's a lot more legalities that you go through to get up there. Yeah.
Have you ever done a hiking trip like that? Well, obviously, like not like Mount Everest, but like.
The tallest mountain I've ever gone up was Mount Timpanogos in Utah. 12,500 feet, I want to say. I went from the bottom all the way to the top. High enough that we started with a group of 14 and only me and 2 other people made it to the top. Everyone else got too altitude sick. When you get high enough, like your internal, like your brain feels the change in pressure. And some people, especially if they live in low-lying areas, like people that live at the equator, they're used to that rich oxygen atmosphere. When they get up that high, they can't really breathe. Like my wife is from Seattle, right? She grew up at 17 feet above sea level, right? So the first time I ever took her to Denver, which is 5,000 feet above sea level, she couldn't breathe. She had a really hard time breathing. She just basically had to sit down in the airport while we waited for our flight.
Would we have trouble, like here in Odessa?
We're about 2,500 plus feet above sea level. You wouldn't have a hard time breathing in Denver, I bet. If you went up Everest, you would. Pretty much anyone would, really, if you live in any of the more common areas.
Why do people get like drunk faster and higher elevation?
Why do you get drunk faster? That's a great question. What does alcohol do?
Doesn't it like slow your metabolic rate?
It has an effect on metabolic rate, but it prevents your cells from absorbing oxygen. Both blood and brain cells cannot absorb oxygen while you have alcohol in your bloodstream. It makes it less effective. So if you're in a place with low amounts of oxygen already, so you're deprived of oxygen, then you need to drink less alcohol to feel drunk. But there's also a problem with that. Alcohol has a much lower freezing point than water. So if you're in a place like Everest, where it's like, I don't know, let's say maybe 0 degrees on a good day, okay? And all your water is frozen unless it's in a thermal container, but you have this bottle of vodka, right? Should you drink that? No, that vodka is at 0 degrees. You drink that, it freezes your throat.
What about like the medicine? I forgot what it's called, Jägermeister. Because didn't they use that one because it was like supposed to be a medicine, and so that's why they used it because they found out it can make you drunk, and that's why they made like a liquor like that.
I don't know.
No?
Yeah, I'm not familiar with that. Interesting, though.
Don't they say that like whenever you drink like alcohol, like you feel warmer inside? Like what's that?
You feel warmer inside because it's disrupting your brain's ability to recognize what's going on with your body. Yeah, drinking alcohol when you're cold is a terrible idea. It deadens your senses and it deadens your response rates. You'll die and not even know if you are drinking alcohol in a very cold environment. Yep. Did you have something to say?
I thought we were under sea level over a basin.
No. So what we are in, that's a great question. We are not under sea level. Just because what we are in is called a basin doesn't mean we are under sea level. Where we are used to be a low-lying area, like a bowl, okay? It used to look, and this is very exaggerated, right? Like this, except this is, 800 miles across. So that's greatly exaggerated, right? But it slowly filled in with sediment over time because it was a low-lying area. And now here we live, up there at the top of all of that sediment that filled in the basin. The basin is the structure we are on. It is not currently a basin anymore, though. Great question.
Has there been like have people tried to get the people on Mount Everest that have frozen before? Like on college?
I'm not sure if anyone has tried body recoveries. I bet people probably would have, but the reason why they are still up there is because it is extremely difficult to get your own body up there and back safely. And so not...
What
Pe-
about by like helicopters?
Helicopters require internal combustion engines to function. Internal combustion requires access to oxygen, which is why internal combustion of your car... Have you ever tried driving a car through water that was too deep? and it died? Why does it die? Because your radiator at the front, or your air intake at the front of your vehicle, doesn't have access to oxygen, believe it or not. Your water is not combustible in your engine, so it intakes the water instead, kills your engine. Okay? Helicopters operate on the same principle of an internal combustion engine to operate those rotors. So if you get high enough, helicopters cease to function.
Why don't they bring their own oxygen up there?
Because that adds weight to the helicopter. You add weight to the helicopter, you need more fuel. You need more fuel, you make more mass. You make more mass, you need more fuel. It's not a sustainable process. And I don't even know if there is a way to deliver enough oxygen to your helicopter to make that efficient. So, yeah. Maybe one day we'll have the technology to do something like that, or maybe one day some Nepalese Sherpa who will decide, yeah, I can bring those bodies down. But as far as I'm aware, I don't know if any have come down. Maybe a few have. Maybe. I don't know. I'm not going to lie to you and say I know for sure, but I know that there are still bodies up there. Anyways, okay, so that's elevation. What about something like distance from a water source? What kind of a difference would that make? What about plants? Why would plants care about distance from a water source? Well, you're right, actually. The closer you are to a surface water source, the more humidity you have in your atmosphere because of evaporation. That'll affect things like temperature, and ambient humidity will change the type of plants and animals that can live there. But also, the closer you are to a surface water source, the more water you actually have in your soil near the surface. Okay? So in a place like this, where we do not have a naturally occurring nearby water source, our groundwater is really low. In a place like Crater Lake, Oregon, the groundwater is really high, right? So is things like humidity. So access to water means a lot to plants and animals, and it also changes things about like groundwater, okay? All right. So here we can see kind of some bands that I've drawn on top of this map we looked at before. We're here in the red is generally tropical with a few minor variations depending on geography. Why is the Serengeti in this kind of in this tropical area that I've written it? Because it's inside of a giant continent. Okay? Remember, the larger your continent, the drier it gets, because the further in you go, the further you get from a water source. So small rainforest in Africa because of the size of the continent inside of our tropical zone. But notice pretty much all of Indonesia is inside that tropical zone with no deserts, because they are smaller land masses and therefore proximity to water is plentiful. Over here in South America, the Amazon fills up most of that space with very little non-rainforesty areas. Okay? Then you go out, and these blue areas, those are your desert areas, but there's a little bit of overlap, and those overlaps include things like Serengetis, grasslands, prairies, etc. Then you get into your straight-up desert zones outside of that. Okay? Just kind of a generalization there. Okay, when I say Serengetis, that means things like your grasslands, savannas. It looks kind of like this, okay? Where there is some water, inconsistent rainfall. Where you and I live is somewhere between what I would call a savanna and a desert. We do get some rain. As a matter of fact, it's supposed to thunderstorm this weekend. I'm so excited. Except I'm having a barbecue with some friends, so that'll be a little awkward. But we can just have that inside. I'll just cook outside in the rain. That's fine. A small one. Yeah, no, I have a tiny little property. But the thing, so we have a tiny little property, right? It's about this big. My house fills in most of that, and then this is backyard. But then there's this massive lot of land on the other side of our back fence that's just empty. It's just grass and weeds and thorns and garbage people throw back there. So I get bugs and snakes and coyotes and stuff that come over my fence and through my fence all the time. It's delightful. Last weekend was spent dumping literally gallons of weed and bug killer along that fence line to try and keep things out for a while. But yeah, it used to be an old oil pad, which is why no one's ever built houses on it. The landowner did not sell it because he's holding out hope probably that someday he can put another pump jack there and make more money off of the oil underground. But yeah, so that's just going to stay there. It's going to be great. I'm just going to keep fighting the bugs in the weeds. But yeah, tiny little porch, tiny little backyard. All right, so as you can see, there are a few, scattered trees. This kind of looks more or less similar to what we have here, except this has more grasses. We are a little more arid than this. We're closer to desert than we are to this, but still not true desert, okay? Then we have forests, and there are a couple of different types of forests, okay? This is a northern coniferous forest. So think Washington State, think Canada, right? Michigan out there, right? Wisconsin, lots of pine trees. You can even actually see these at higher altitudes in places like New Mexico, okay? Lots and lots of pine trees out there, okay? So coniferous forests tend to occupy higher latitudes, so closer to the poles. Also lower latitudes, I mean, no, that's still pretty high, but down in the southern hemisphere, okay? And colder climates. They tend to respond better and grow better in colder climates, so higher altitude areas, okay? So high latitude, high altitude areas. And then you've got temperate forests. And this is the sort of thing that you would expect to find not in a rainforest zone, but in your more temperate sort of southern areas like Georgia, for example, has a lot of these. Alabama, North Carolina. You go to Louisiana, you see a bunch of this. Southern Texas would look like that, okay? And then when you go real far north or real far south, you get tundra. Tundra is where you get a lot of permafrost. Permafrost, remember, is where most of your soil stays frozen year-round, but only the top few inches ever actually melt from direct sunlight. That's not really enough for a root system for most plants, and so you don't get a lot of plants out there. But what you do get is a lot of moss. Patches of moss that grow on top of the permafrost when those top few inches of soil melt. Okay? They can grow in those soils. Which is actually very interesting. This kind of ties into something that we're going to talk about later on next week. Have you guys heard about these de-extinction companies? They are companies. Yeah, exactly. These are the companies that their specific agenda is bringing back extinct animals. Now, I taught you a little bit about genetics when I taught you about adaptation through mutation, but I haven't finished teaching you all about it. So some of the things I'm about to say will make more sense next week, but it's kind of relevant to this. So there is a company that is trying to bring back, and these bunny quotes will make more sense next week, okay? Bring back woolly mammoths into northern Canada and northern Siberia. Why would they want to do that?
Imagine how much protein's on
It's not for hunting. Now, will it eventually lead to that? Possibly. The American bison, right? Almost went extinct. There was only one herd of those guys left. And then they became protected. They were one of the endangered species that were classified as endangered when, who was it? Who instituted the National Park System and the Endangered Species Act? It was Roosevelt, I think. Yeah. When he classified them as such, stopped hunting them, and now we have so many American bison running around the middle of our country that you can buy a hunting tag and go hunt them. I can go and buy bison jerky on Amazon right now. I have eaten bison burgers in Wyoming. Okay? They're actually really good. Huh? The meat tough? I mean, a little tougher than cow, but not notably different. Bison steak is pretty good. Bison burgers, they taste pretty good. You know, I've eaten a lot of weird stuff. You guys ever had alligator? Alligator's really good too. No, it tastes like stringier chicken. Okay. I've eaten rattlesnake. Rattlesnake's really good. I've eaten snails. I ate this Filipino dish called dinuguan, which is pork. It's pig blood mixed with rice. It's actually pretty good. Yeah. Balut is another Filipino dish. If you've ever heard about taking those eggs, the duck eggs, and then
Yes, and it's like they're still there.
Yes, it's a dead duck inside, and you just swallow it because its bones haven't formed, and so it's just really rubbery. I've had that. If there's an interesting, weird international dish, people are like, hey, you want to try that? I'm almost always like, yes.
Have you tried frog?
Frog? Yes, I've had frogs.
Did you like it?
Actually, yeah, it was yummy.
I've tried them too. They were not good.
You did not like it. Depends on how they're prepared, right? Let me tell you, the French know how to make frogs. They make yummy frogs to eat. Okay, back on topic. So why would we want to bring mammoths back? Not to hunt, but my point with the bison is eventually one day, maybe in a couple hundred years when the populations are big enough, maybe you could be open season on hunting the mammoths. But that's not the purpose.
Would that be so cool? Imagine how much meat you could acquire.
I mean, sure, but that's the same philosophy our ancestors had when they got wiped out in the first place. No, it's not for the tusks. The reason why they are concentrating on bringing back woolly mammoths right now is because of this. So, since the end of the last ice age, the mosses in the northern hemisphere, in the tundra areas, have started getting out of control. It's completely throwing off the ecosystem, drowning out grasslands, tons of moss everywhere, and the more the permafrost melts, the more mosses there are, right? Not leaving space for grasslands to develop. So, here's the thing. Because we can see inside the stomachs of a lot of the mammoths that were frozen in that permafrost, we know they not only ate grasses, they ate the moss too. So here's the thought. If we bring the mammoths back, they start eating the moss situation eventually comes back under control and the ecosystem stabilizes. They think that maybe when we overhunted the mammoths to extinction, we threw off the ecosystem because they were holding the moss in check. So that's one of the major driving factors behind why they're trying to de-extinct the mammoth. How is it possible? Okay, so I go into all of this next week, but do you guys want me to give you the cliff notes right now? It's kind of like that. So Jurassic Park got some things right. Okay, Jurassic Park basically said we have most of a dinosaur DNA strand from DNA that was trapped inside of a mosquito in amber. Okay. Couple problems with that. DNA does not survive, no matter how trapped in amber it is, okay? Because it's already been exposed to oxygen in the living organism, which means it is already in the process of breaking down. It does not take long at all before the DNA is totally wrecked, destroyed. So you can't get DNA from amber, but we get DNA from a much better source, a living source. Dinosaurs alive today. Birds. Yes, birds are dinosaurs. They're the only type of dinosaur that has survived the extinction. Avian dinosaurs, we call them, a classification that came from the same ancestor as things like Velociraptor. Okay, they share the same common ancestor, so they share a lot of the same DNA from before they split. So we can take bird DNA and we have mapped it and experimented with it to the point where we know what DNA combinations we can turn on, flick off to bring back the same traits that common ancestor did. Because what happens over time, as you adapt away from a trait that you don't need anymore, or as you bring in a new trait that you have through mutation, other things get flipped on and off, right? We no longer have the long arms that chimpanzees do, even though we share the same common ancestor. We no longer have shells on our backs, even though we share eventually, far enough ago, a common ancestor with a beetle, right? We don't have those things because we've evolved away from those, but you know what? Those are all in our DNA from our common ancestry. So we know how to flip those on and off. And when I talk about this more next week, I'll show you some cool pictures. We've actually done this in labs, and we've made dinosaur chickens. Chickens with teeth and claws and all of that. It's currently illegal to let those things hatch because you're effectively making a brand new species out of old ones. So it's against international genetic law to actually let those things hatch and do that. But we've made them in labs. We've actually made inside of an egg, and we've we've scanned inside of the egg and seen the teeth and claws and everything on the chicken embryos. We know how to do all of that now. So what they are doing is they're basically taking Asian elephant DNA and turning on the old genetic switches that it shared in common with woolly mammoth ancestors. So that's why I went woolly mammoth and de-extinction. We're not bringing woolly mammoths back. They're gone. It's sad, but it's true. They're dead. They will never come back to this world. What we are doing is we are taking Asian elephants and we are flipping on the switches to give them the characteristics that their ancestors had in common with woolly mammoths. So we are effectively making a brand new species and calling it a woolly mammoth to fill the same ecological niche left behind by the old ones. Okay? So it's not true de-extinction. It's species invention. Interesting, huh?
Artificial selection.
It is a form of artificial selection. We are choosing what traits we want to be present in an organism. Can you guys think of any other examples that we've done this with? Dogs. Oh man, we're going to talk all about this next week. But dogs. Every single type of dog out there in the world is a fabrication of human genetic invention and interference, I guess you could say. There never used to be any dogs on this planet. Dogs only exist because of us. They came from wolves. We chose how to make dogs by selectively breeding wolves. And now we have hundreds of, not species, all dogs are the same species, which is weird to think of a Dachshund, a Greyhound, and a Chihuahua being the same species. But they are. They're just different genetic variations based on the traits that we choose to carry forward generation to generation. Okay? So anyways, that is why they are bringing back woolly mammoths for this situation. The dire wolves that they made were kind of the first big thing. They made woolly rats a few years before that, which is very funny. Ice Age rats that are thick fur on them. Then last year they did the whole dire wolf thing, which made everyone in a tizzy. Like, oh my goodness, dire wolves. They're not actually dire wolves. They are, I believe, timber wolves, where they genetically modified the embryos to express traits they had in common with the ancestor of dire wolves. Not even dire wolves themselves, the same ancestor that timber wolves and dire wolves had in common. Okay? Okay.
Have they ever hatched one of those chickens? Like I know it's illegal, but have they ever, have you seen one hatch?
If someone can do a thing, someone in the world has done it. All of the responsible labs that published on it did not hatch those chickens. But you know there is some lab in the middle of nowhere in Montana or Siberia or China where they've been playing around with genetic modification and there's an army of little chicken dinosaurs running around for testing, right? You know someone's doing that.
Do you think that they'll actually try to bring it back like dinosaurs? Or like
I know people are. There are very famous scientists, genetic biologists, and geologists, paleontologists, who openly advocate for trying to recreate dinosaurs out of birds.
what's the purpose for that?
Entertainment. It's essentially Jurassic Park. There is no purpose that a chicken dinosaur could serve in our world's ecosystem. We are 65 million years beyond when dinosaurs were relevant to our world. So the only reason to bring them back would be for novelty. Like, have you guys seen the most recent Jurassic Park movie? They make a point in that movie of talking about how most of the dinosaurs that escaped the islands are dead now. They just died. They could not adapt to the world the way that it is now. It's much colder. Its atmosphere has changed. Like, they could not survive. So most of the dinosaurs that escaped in the first 4 movies are all dead. So unfortunately, I think that's how it would go. They are not meant to live in the ecosystem the way it is now. So there's no point in bringing them back other than pure curiosity and entertainment purposes. Oh, we did this. We could do it, so we did it. And that never really ends very well. There needs to be some sort of purpose behind it. Yeah, Alma.
I was gonna ask, have you heard about that movie about like the people peptides? Like about, because they're naturally occurring amino acids and people are like injecting, like it's seen it a lot like in the gym community, people are like injecting them into themselves just like help boost like certain actions. Like I know like there is one that's like really prevalent, it's called retinol. It's kind of a GLP then it's like unregulated, but people are still getting them like on gray markets. And
Yeah.
stuff like that.
Gray markets are getting big. If you're not aware of what this is, so there's this agency called the FDA, the Food and Drug Administration. Its entire job is to safety clear food and drugs, right, for general use. If that's a United States organization, though, and there are some ways to get around that. One of which is the gray market. You get something certified in another country, and then you can just sell it.
Buy it from China.
Yeah, you can buy it from China, and it's not FDA certified. And so even though they have cleared it, so it is legal in some country, it may not be legal in ours. A black market, you're selling something that is blatantly illegal. A gray market is something that walks the line. It hasn't been approved here, or it has been preliminarily approved. Like I saw a product the other day that said FDA cleared. It didn't say FDA certified. I'm like, okay, so they didn't say no, but they certainly didn't put their stamp on it. That's more of a gray market sort of thing. Okay, so yeah, GLPs are really big right now for weight loss. I think we're going to figure out in time what the long-term effects of those are. It's still very new on the market. But
Like because I know people that are taking them and stuff like that, and like they're taking, because my mom, she has diabetes, right?
Mhm.
And so like I know like a lot of people like in my personal life that take them, even though like it's not healthy for them, because that's just gonna mess up like their insulin levels. And
Yeah.
It's gonna make it harder for them. It's gonna make it harder for them to like lose weight later on. 'Cause
Yeah.
it's just gonna mess with their insulin levels.
And that's the problem with taking any supplement for weight loss, is it does not have a long-term effect. It helps you lose the weight right now, but it doesn't eliminate the ways that you gained the weight in the first place. So it's much better to develop healthy habits. It takes longer to lose the weight, but it will last for a heck of a lot longer too, because those healthy habits will stay after a medication runs out. Okay. Anyways, okay, we talked about tundra. All right. Plants. Plants are extremely valuable in interpreting these past environments. Why? Well, plants absorb a lot of the things from the environment that they live in. The water, the atmosphere, all of that. This includes the isotopes that are present in those environments as well. Remember how I told you about carbon 13, 14, 12, all of those isotopes? Remember I told you about oxygen has isotopes, oxygen 16 and 18? Well, just looking at those two types of carbon and oxygen isotopes, you can get some very valuable information about the environment that that plant lived in. So if I have a well enough preserved fossil plant, I can get information using those isotopes. For example, which one is more massive, oxygen 16 or oxygen 18? 18 has 2 more neutrons. It's an isotope of oxygen 16. 2 more neutrons, more mass. On Earth, heavier. So if that oxygen 18 is in a water molecule that evaporated out of the ocean and it cools off, that whole bunch of water in the atmosphere cools off, which water molecules are going to fall first? The ones with more mass or the ones with less mass? The ones with more mass will fall first because they're heavier, right? So that means that we see an increase in the quantity of oxygen 18 isotopes in the rain at the equator, and an increase in the amount of oxygen 16 isotopes the further you get away from the equator. So if I look at the ratio of oxygen 18 to oxygen 16 in the plant fossil I'm looking at, that tells me how close to the equator it was, essentially, because it'll tell me how much oxygen 18 was in the water it absorbed. You follow that logic? Same thing with carbon 12 and carbon 13, except those are more commonly associated with temperature variations. Carbon 14, only made when you burn fossil fuels. So this is how we know how much carbon dioxide we've actually produced since the Industrial Revolution. We can track the absorption rate of carbon 14 in plants. There are plants that have been around for the last couple hundred years, right? And we can look at samples from those plants to see that hockey stick in the increase of carbon 14 in the atmosphere, because it's only produced from burning fossil fuels. Okay? All right, as far as marine environments go, so we're talking about out in the ocean now. Some of the factors that most influence marine environments are things like currents. What is a current? A current is a direction in the movement of water that can be associated with wind patterns, and often is, but also has to do with temperature variation. Okay? So we've got warm currents and cold currents. Okay? Warm water flows through from the low latitudes near the equator, cools off, and then flows back down south towards the equator. Okay? So the constant cycling of warm water and hot water in our ocean makes a lot of this current activity. And let's see, I have a picture right here. This shows you what the most common prominent currents are. Here out in the Pacific, you see we've got a lot of warm water. It's the Pacific, the warmest ocean, most people consider it, okay? But once you get up here, it starts to cool off. Why? Distance from the equator, proximity to the poles. Down south here, cools off. Same reason. Okay? It's constantly cycling around. Warm, cold, warm, cold, warm, cold, warm, cold. Tides. Tides are a big factor too. When the tide goes out, it leaves shallower water or no water. And that's going to affect the kind of things that can live in that area. Tidal flats. We learned about tidal flats, right? Lagoons, typically, when the water gets sucked out by low tide, it leaves very little or no water on the tidal flat. So your organisms need to adapt to survive in that environment. And many have. Then the water comes right back in during high tide. Tides being caused by... The moon is the largest force nearby, but not the only one. It's also the sun. So tides are not caused only by the moon. They are caused by gravity. It's gravitational pull. Okay? No, it's okay. It's okay. I was looking for a broader answer. You are all right. I'm just looking for the broader answer. What do the moon and the sun have in common? They both have tidal pulls. Remember, tidal pull is not just a reference to the ocean. Tidal pulls happen in space. It's a reference to the pull of a mass, aka what we call gravity. Huh? Jupiter on Earth?
Yeah.
Very small one. Yes. Jupiter is the second largest mass in our solar system, so it has a small effect on Earth, but nothing compared to the pull of the moon or the sun. Yeah, it's far enough away most of the time. Every now and then we pass kind of close to it, not again enough to make a huge difference. Slightly measurable though. Okay. Then there's salinity. You guys remember what the word salinity means? Yeah, it's the salt content in your water. Have you guys ever heard of this place called the Dead Sea? It's out in the Middle East. No? Huh? You think I told you about it? It is a body of water. It's a sea, a large body of water that is so salty. The shorelines are made out of salt, caked in salt. Nothing lives in there because it is so salty. Well, we thought. A couple years back, some folks went diving down to the bottom and they found what appear to be bacterial colonies living at the bottom of the Dead Sea. Other evidence, further evidence, that bacteria really can live anywhere. Right? They live in the saltiest conditions on Earth. They live in the hottest conditions. They live in the coldest conditions. Bacteria in space? Yeah, sure, right? Why not? They live in all of the most hostile places here. So, it is so salty that you can lay on your back in the water and you won't sink. At least not more than an inch or two, because the saltier the water is, the more buoyant you are in it, okay? The closer your density is to that of the water because of how much salt is in it. It is super salty, okay? That's the saltiest water on Earth. Then you've got fresh water, which is very little salt to no salt whatsoever. Fun fact, this water that we buy from the store, do you notice how it says with flavor-enhancing minerals in it all the time? Or it'll sometimes say added electrolytes. Do you know what that means? They add a little bit of salt to your water. Why would they do that? They market it as flavor enhancement or electrolytes.
To dehydrate you so you can drink.
Yeah, they want you to feel thirstier after you drink it, so you drink more. It's Fun little market game there. Okay. All right.
Microplastics in it.
Huh?
It's all microplastics.
Microplastics, yeah. Oh, let's not get started on microplastics. Okay. Our ocean, we separate it into different zones, okay? So these zones are separated by how close to the surface they are, aka how much light there is available for the things that live there. The organisms that live in the ocean are differentiated prominently by things like access to light and temperature variation. The deeper you get in the ocean, the colder it gets. Okay, the closer you get where it's lighter, there's usually some more heat too. So this part that's next to the coastline, okay, we call this the tidal zone, okay, where the tides come in and out, the closest you can to land. That's the tidal zone. Then we have the photic zone, which is the furthest extent from the surface all the way down, the furthest extent that light can penetrate, okay? Anywhere from 300 to 600 feet, like I have here, depending on how clear your water is. If it's not very clear water, about 300 feet. The clearest water, though, that sun can go down as far as 600 feet. And that's called the photic zone, aka the furthest that photons can go. Okay, the particles that come from the sun, the light particles, okay? Then you have the benthic zone, or benthos, which is everything below the photic zone all the way down to the bottom, okay? Our food chain is very tied into those zones. Phytoplankton, for example, these are photosynthesizing planktonic animals, okay? Dinoflagellates, coccolithophores, diatoms, all sorts of fun names, okay? But they live in the photic zone. Why? Because they photosynthesize. And without water, or without sunlight, they won't be able to photosynthesize, okay? They are the bottom of the food chain for pretty much the entire ocean, with the exception of the chemosynthetic organisms in the bottommost parts of the ocean, okay? But what eats the phytoplankton? Zooplankton and the little babies of all of the other animals, okay? So phytoplankton are the bottom of the food chain. Then we have our zooplankton, which are essentially planktons that have evolved to be the carnivorous type, okay? So these guys will eat those guys. Pelagic organisms, that means that they just kind of float around in the ocean current. They don't direct themselves or the direction that they go. They just kind of float around, okay? Hello? It froze on me. There we go. Did I skip something? No, I did not. Okay. So, those are your pelagic organisms, the ones that just kind of float freely in the water and get eaten by everything else, okay? So those in turn get eaten by either grazers. Those are the ones that eat stuff off the bottom of the ocean, algae, bacterias, the planktons that live down there. Suspension feeders, which are the ones that have kind of those tentacle sort of things like sea anemones and corals and stuff and sponges. Then they'll just capture the planktons out of the water and eat them that way. Deposit feeders, those will eat kind of the leftovers that sink to the bottom of the ocean. Anything organic that kind of goes to the bottom, like snails will do this. Okay, snails are deposit feeders. So they'll just kind of go around the bottom of the ocean and eat the organic remains. So dead stuff, poop, all of that. They'll ingest all of that, slurp whatever they want out of it, and then expel the rest. Then you have your larger carnivores that eat all the rest of those. So your ammonites and your sharks. Okay, so and your whales. Okay, so here we have a generalized food chain. Phytoplankton gets eaten by the zooplankton. Zooplankton gets eaten by the small fish. The small fish get eaten by the squid and the larger fish. Those in turn get eaten by the whales and the sharks, so on and so forth. Any leftovers that fall out of the photic zone eventually make their way down to the benthos and are eaten by your grazers and your deposit feeders. Huh? Tripod fish? Huh? So those are the benthic ones that live at the bottom there. Grazers, suspension, and deposits. Okay, so here we have the same thing I showed you earlier, but I'm just kind of going to hesitate on this for a minute. Okay, water temperature is largely dictated by proximity to the equator and therefore where the currents are going as well. Okay, so our Equatorial area, we call it the tropical zone. Your warmest water is going to be there. Above and below that, your subtropical zone. Above and below that, subarctic and subantarctic zones. Do you remember the little rule of thumb I taught you for remembering Arctic from Antarctic? Yeah. What does Arctic mean? Bear. Right? Bear. Where are the polar bears? The North Pole. So that's the Arctic. Where are there no polar bears? The South Pole. Antarctic, aka no bears. Okay? And then one more note about salinity. For something to be considered saline, it is between 30,000 and 40,000 parts per million of salt. That's a lot of salt. Don't drink that. Okay? It's yucky salt. More than that, and we have a state called hypersaline, like the Dead Sea or the Great Salt Lake in Utah. Okay? If it's too fresh, we call it brackish. There are organisms that have adapted to live in both. Clearly, we found the bacteria in the Dead Sea. They live in hypersaline waters. Okay, what about brackish water? Lots of things have adapted to live in brackish water. There are even some sharks that live in brackish water. Lots of fish, lots of shellfish, lots of organisms have adapted to live in brackish water. Where would we find brackish salt water? Sure, in the ocean, but where? Sure, I'll give you a hint. Where would we find salt water where fresh water is diluting it?
Where it ends up, where the stream ends.
Yeah, river deltas. I heard that word over there. Nalma was getting to it. Okay, yeah. Where the river meets the ocean, we get a delta. That's fresh water running into salt water. That's where you'll get your brackish water. Yeah.
We also get brackish water around like Antarctica and stuff, or like around like where the ice melts and stuff.
Yes, there is a narrow area, a very thin area around bodies of ice that are melting that become brackish. Yes. All right, so now let's talk about fresh water for a second before we end. We have in fresh water less than 500 parts per million of salts. Okay, so anything with less than that is going to be considered fresh water. Now, here's the tricky bit with fresh water. There is far less fresh water on our Earth than there is salt water, right? Which means that the historical fossil record for fresh water is far, far smaller. We don't have as much information about fresh water. So it's difficult to know the evolutionary history of freshwater organisms going far enough back. Okay, more recent times we can, but far enough back, very difficult to tell. Okay, because freshwater systems are smaller than the ocean, they also have less diversification. We see less evidence of adaptation. The communities are smaller, populations are smaller, and it's difficult to draw correlations with bodies of freshwater over time. Okay.
Do you think that the animals that used to live in more salt-like water, they adapted to live in like fresher water?
Oh, they definitely did. And we will talk about that in Module 3. That's absolutely something we cover, is the adaptation from moving from salt water into fresh water. Okay, that's what I got for your lecture today. Any questions? No? Well, I'm going to go ahead and give you guys Lab 3 now. So Lab 3 is open, and I'm just going to give you a quick run through this. Lab 3 PowerPoint has every piece of information you will need for this lab. I'm not going to go through everything here, okay? Because you have access to this. This is a resource for you. I'm just going to give you the quick version, okay? So this is a lab where you're starting to learn about invertebrate fossils. Remind me, what does invertebrate mean? No backbone, exactly. So we're going to be talking about things with shells, exoskeletons, and chitin, okay? Just the things you see on this slide here, those are only a few. It's going to be this branch of our phylogenetic tree there. We're going to focus on the organisms you see there in that circle. And then this is, like every slide here is just going over the basics of the different types of organisms. The difference between brachiopods and bivalves, for example. Okay? They look very similar. They're both shellfish. You could throw both of these in a pot and have a yummy seafood boil. Okay? How would you be able to tell the difference? Easiest way to tell the difference? Shell symmetry. Okay? A bivalve, aka something like a clam or an oyster, is going to be asymmetrical when you look at it from the top down. Those two halves are not exactly the same, right? This half and that half. But when you look at it, shells half to shell half, lengthwise like this, you'll notice that both of these halves are exactly the same. So it is symmetrical top to bottom, not left to right, top to bottom symmetrical. Brachiopods are the opposite. This is a brachiopod shell. Notice that when you look at it from the side view, they are not symmetrical. When you look at it from the front view, they are. So brachiopods are symmetrical left to right. These are not. These are top to bottom. Okay? Easiest way to tell the difference between a brachiopod and a bivalve, especially in fossil format. So your lab is going to ask you a few things. What is this? What is that? When did we first see these things show up in the fossil record? How would you know that? Well, I give you the dates right here. Brachiopods showed up 541 million years ago, and we still have them. These guys, 500 million years ago, we still have them. So you will just select the appropriate time period for whenever that corresponds to, okay, on your assignment. Huh? Yeah, bivalves, clams and oysters are both bivalves. Yep.
Have you ever had them like raw?
Yes. Yes, I have. An acquired taste for some people, but yes, I actually really enjoy seafood. I grew up having amazing seafood. I lived next to the ocean every day of my life until I was 16. Okay. Nautiloids and ammonoids. These are also two things that are easy to confuse with each other. They both have these curled shells, like so. Okay? Best way to tell the difference between them. When you're looking at a nautiloid, the sutures, or these seams, these separations between the parts of the shell, are always going to be pointed towards the opening. Okay? This is the opening down here where the animal would have, like, its tentacles would have come out of. Both of these, by the way, are cephalopods. Think squids in a curled up shell. Okay? Nautiloids, these are still alive today. And I have the shell of one right here. This is a nautiloid shell. Maybe you recognize it from that look. It's just half of one. But you'll notice that the sutures between each chamber are curved toward the opening. Whereas in an ammonoid, they are a little wiggly, but they are generally curved away from the opening. Easy way to tell the difference right there. Okay? Let's see, this gives you all the information there. The kingdom, phylum, class, yada, yada. Okay, talk about the different types of corals. There are lots of different corals that we've learned about, or that we will learn more about as the class goes on. Horn corals, or rugose corals as they're called. Tabulate corals. They each have their own different thing. I give you a description of each of these. Scleractinian corals. These are the types that our coral reefs are made out of now. Sponges, which we have now and have had in the fossil record for a very long time. Bryozoans, which look kind of like corals but are completely different animals. Gastropods like snails, cephalopods. Let's see. Trilobites. You guys remember we learned about trilobites, the kind of big bug-looking ones that can curl up on themselves to protect themselves. They have those curling shells. Give it a second here. Okay, here we go. So just like modern-day pill bugs, or roly-polies, as you may know them, they were able to curl up on themselves. This is one that died in that curled-up orientation. Okay? But these are arthropods, ancestors to insects, you can think of them.
If we wouldn't have found that one further, would we have known that they could have?
I mean, it has a segmented shell, which generally implies some level of flexibility, but we probably wouldn't have known that they could do it to that extent without finding the fossils, yeah. Eurypterids. These were also arthropods, just like the trilobites, except they ate the trilobites. These were some of the larger predators. Matter of fact, they're the largest arthropods that we know about. They could get about 6 feet long. Okay. Barnacles. These are crustaceans. Actually, the closest relative to barnacles, crabs. Okay. You wouldn't know it to look at it, but they are very closely related genetically, except one decided to evolve legs and one decided to stay put. Okay. Otherwise, very, very similar structures there. Insects. Okay. These are also arthropods. Winged insects, all of those involved here. We're going to talk about each one of these groups in more detail in Module 3, by the way. This lab is just supposed to give you some preliminary information about them before we get there. Okay. Different plants. Plants have had an interesting evolutionary history. They started off in the water as something more like a seaweed, and then they moved out closer to land as time went on. And then they developed something called vascularization, which is the ability to pump water through their tissues instead of having to remain in water constantly to get that sustenance. Okay, so once they developed vascularization, they were able to leave the water and move out onto land and have the rigid structures for trees and all of that. Okay, so we see the first actual plants on land about 470 million years ago. And then the first big ones that had fully moved onto land about 445 million years ago. 425 million years ago is when vascularization really took off, so they were able to get further from the water. And then gymnosperms appeared 319 million years ago. Now, gymnosperms are really cool because they had seeds. Before, plants more or less spread through spores. If you've ever seen how a fern reproduces, it spreads a bunch of spores from pods. The spores float through the air, land somewhere, and grow a new fern plant. Well, gymnosperms, like Christmas trees, right? Coning plants, conifers, right? Pine trees, essentially. They developed the ability to have a seed. We'll talk about how amazing the seed was later on, but it allowed the trees to start spreading further and further from water because they didn't rely on constant access to water to keep the spores alive. And then angiosperms, so flowering plants, showed up about 140 million years ago during the Cretaceous, which was the last age of the last age of the dinosaurs. They showed up a while before the dinosaurs went extinct. Grasses show up 129 million years ago. Yeah, grasses were not around for all of plant life. Matter of fact, what we have today as grasslands were probably fernlands for a long time. Ferns occupied that niche until grasses came around and filled it. Okay, so you've got some questions to answer. You've got some observations to make. You're going to consult this PowerPoint. You're going to get familiar with those organisms. You may want to hold off on submitting Lab 3 until you also look at the Lab 4 PowerPoint. There's a little bit of crossover there. Lab 4 also may have a little bit to do with Lab 3. Okay, so a little bit of crossover between the labs there. So don't stress about getting it turned in now until you've looked at the all of the data for both of those. Okay? Questions? All right. Well, if there are no questions, I will end the recording here.